All right, so now we're going to talk about Galerkin discrete Hamiltonians. Okay. So if you recall, it's like the Galerkin discrete Lagrangians were constructed by taking the characterization of the exact discrete Lagrangian and then approximating it by taking variations over a finite dimensional function space and by replacing the integral by a quadrature approximation. So we're going to do something very, very similar with the Galerkin approximation of the exact discrete Hamiltonian. Okay, so if you recall, you have this HD plus exact, which depends on, say, Q0, P1, and implicitly depends on H, right? And then this is equal to the extremum over curves QP, which are twice differentiable, and they map from 0 to H to T star Q. With appropriate initial conditions, so Q0 is Q0, and then P at H is P1. Okay, and then you are extremizing over essentially, let me just call it P1 Q1 minus the integral from 0 to H of P Q dot minus H QP dt. All right. All right. So you might expect then, it's like just from looking at this form of it, that when you do this Galerkin construction, you need to specify a function space both for the position and momentum variables. But as it turns out, it's like that's not actually true. If you actually go through the process for doing this, you find that you have to specify the function space for the positions, but not for the momentum. And if you wonder why there's this distinction between the two, more or less it has to do with the fact that when you look at the object which you're extremizing over, on the one hand you have Q dots, but on the other hand you don't have P dots. Okay, and so as it turns out, then all you really need to know about P happens to be the value of P's at the quadrature points, and that is uniquely specified by the sort of this variations which you take. Okay. Whereas if you were to try to do the same thing for the Q's, you also happen to need to know what the Q dots are at the quadrature points, and then that requires you to know something about where, which function spaces the Q live in. Okay, so that's more or less the distinction. So if you want to have a computable discrete Lagrangian, sorry, a computable discrete Hamiltonian, right? You have to basically choose the same things you would have chosen to construct a discrete Lagrangian, which is that you would need to choose some finite dimensional space, okay, from the interval 0 h to q, right, which is contained in, so it's contained in what we had called C, right, and C, if you recall, it's like includes both the regularity assumptions, right? So this is basically, so it includes sort of C2 regularity plus the boundary conditions. Okay, so so this space already sort of includes the boundary conditions, if you will. So anyway, you choose this finite dimensional subspace of this appropriate space, and then you also use a quadrature rule, right? So you choose this and a quadrature rule. Right, which sort of basically says that if you take an integral of f of x dx, right, you approximate it by h times the sum of bi f at cih, something like that, right? And that integral is from 0 to h. Okay, yeah, so that's what you need to do. So then you have a computable discrete Hamiltonian, which I denote by hd plus. It depends on q0, p1, implicitly depends on the time step h. And then this is equal to the extremum over sort of what I call qd, which is in this finite dimensional subspace, CDS. Okay. 0 h to q. Okay, and then you want that the pi's are in q star, right, which is the appropriate dual space to q. Okay, so we have to be a little bit careful here. So you have to sort of basically assume you're working in a vector space, because if you weren't working in a vector space, it's not really possible to specify a momentum without the sort of the base point, which is the position. Okay, but if you're in a vector space, then that's fine. It's like we can identify everything. It's like appropriately. So anyhow, so what you get then is you extremize over P1 because that's specified, right? P1 is specified, and then you have QD, which is this curve. You evaluated H, right? Minus then the quadrature approximation of the integral, so H sum of I, right? And then you have basically P at CIH. Okay, QD dot CIH minus H at QD CIH P at CIH. Okay, so again, it's like formally I've written P at CIH with an understanding that these PIs are really P at CIH. Right, so that's it, where the PIs are equal to P at CIH. Okay, so the point, if you will, is that you're varying over these values. It's like and the extremization or stationarity condition will allow you to pick out those distinguished values of PIs. Okay, all right. So anyway, so what this is sort of suggesting, if you will, is that your discrete computable discrete Hamiltonian or Galerkin discrete Hamiltonian, right, is just predicated on two choices, one of which is the finite dimensional function space, which approximates the position trajectories, and a quadrature rule. So it's worth observing, of course, that those are exactly the same choices one makes when constructing a Galerkin discrete Lagrangian. Okay, so it's natural to ask that if the following question: if you were to make the same choices of a quadrature rule and a finite dimensional function space for the position trajectories, right? Do the two methods, which are induced by the discrete Hamiltonian and discrete Lagrangian respectively, do they agree with each other? Assuming, of course, the Lagrangian and Hamiltonians are hyperregular and there's this one-to-one correspondence between the Lagrangian and Hamiltonian mechanics. And as it turns out, that is indeed the case. Okay, so there's a proof of this, which I won't go into, but if you're interested in that, I'm happy to point you to the reference. But let me just sort of state the result as it stands. So there's the following proposition, which says the following, that if the continuous Hamiltonian right, H QP is hyperregular. So hyperregular just means that the Legendre transform is globally invertible. Okay, and we construct the Lagrangian LQQ dot, right, by the Legendre transform. Then the sort of Galerkin discrete Hamiltonian, well, Galerkin Hamiltonian variational integrator. And the Galerkin Lagrangian variational integrator. Associated with the same choice of basis functions So I've chosen to parameterize, if you will, this function space by some choice of basis functions. And numerical quadrature rule. Sort of I equivalent. Okay. So, if you will, what this is more or less saying then is that if you were to choose this Galerkin construction for the discrete Hamiltonian, and then sort of the analogous thing on the Lagrangian side, then the diagram, which I will write down, it's like commutes. Okay. So, more or less what this is saying is that if you have a Hamiltonian, right, and this is related by the Legendre transform to the Lagrangian, and then you have this kind of Galerkin variational integrator construction. Okay, to get, for example, the discrete Hamiltonian or the discrete Lagrangian, right? Then those two things agree in a natural way as well. Okay, right. So the diagram more or less commutes, and you get the same method when you have hyperregularity and when you're using the same choice of basis functions and quadrature rules to construct each of these Galerkin variational integrators on either the Hamiltonian or Lagrangian side, right? And if you do that, then the discrete flow maps which are generated agree with each other and they're equivalent in sort of the obvious sense. All right, so let me just stop here for now.